Another example. So consider the vector space R, so the usual set of real numbers with the usual addition and multiplication, and the vector space R plus, the set of all positive real numbers. So this vector space was given in GYHD4. So in this vector space, vector addition is given by this, okay, the sum, the quote-unquote sum of two elements in R plus is equal to the usual product, to their usual product. And if K is a scalar and X is a vector in R plus, the scalar multiple of X by K, okay, is the kth power of X. Okay. So again, in R plus, vector addition is not the usual addition. Scalar multiplication is not the usual multiplication. Okay, these are the definitions for the vector operations in R plus, the set of all positive real numbers. Okay, so suppose L is given by L of X equals e raised to X. So e is the natural number. So L of X is the exponential function. Okay, so let's check if this function defines a linear transformation of R into R plus, the set of all positive real numbers. So the first condition, or for the first condition, we take two arbitrary elements of the domain and compute L of X plus Y, L of the sum. So by the definition of L of X plus Y is equal to e raised to the sum X plus Y. By law of exponents, this is just e to the X times e to the Y. The product of e to the X and e to the Y, which, as we defined, for R plus is the vector sum, okay, of e raised to X and e raised to Y. Okay, so by this rule, with X equal to e to the X, Y equal to e to the Y, following this rule, we may write this as e to the X vector sum e to the Y in R plus. And e to the X, of course, is L of X, e to the Y is L of Y. So we see that L of X plus Y equals L of X plus that's the sum in R plus, no? In this codomain, L of Y. So the first condition is satisfied by our L. Let's see if the second condition is also satisfied. So consider a vector X here and a scalar K, an arbitrary real number. So L of Kx, by definition, is e raised to Kx. Okay? So L of Kx equals e to the Kx. But again, using the law of exponents, you can write this as the kth power of e to the x, kth power of e to the x. But following this rule of scalar multiplication in R plus, the kth power of e to the x is equal to the scalar multiple of e to the x by k. Okay, so we follow this rule to write this as this. That's the scalar multiplication rule in R plus as indicated. And as we know from the definition of L, e to the x is equal to L of x. So the image of a scalar multiple of a vector in R by k is equal to the scalar multiple in R plus by k of the image of x under L, showing that the second condition is also satisfied by the exponential function. So we conclude that L is a linear transformation of R into R plus. consider the vector spaces P2 and P1. Okay. Consider the map L from P2 to P1 given by differentiation. Okay. L of T is the derivative of P with respect to T. So we can check that L is a linear transformation from P2 into P1 using the rules of differentiation of polynomials. In other words, for any PQ in P2, L of P of T plus Q of T is equal to the derivative of the sum, but we know that the derivative of the sum is equal to the sum of the derivatives. But this guy is equal to L of P of T. This guy is equal to L of Q of T. And if C is a scalar, L of C of P of T is equal to the derivative of C P of T. But because C is constant, because it's a scalar, we can take that out of the function being differentiated. So we can write the image of C P of T under L as C times P prime of T. But P prime of T is L of P of T. So we see that the two conditions in the definition of a linear transformation are satisfied by this differential operator, okay, or this function given by differentiation. So it is a linear transformation of P2 into P1. Here are other examples. For a fixed positive real number R, a function from R2 to R2 given by L of P equals RV, okay, is a linear operator on R2. So this function L acts as scalar multiplication of a vector V by the fixed real number R. So I leave as an exercise to show that this is a linear transformation from R2 into R2, or a linear operator on R2. Geometrically, we can describe this function L as follows, depending on the value of R. If R is greater than 1, the effect of L on the plane is that it stretches on the plane. So in that case, we call L a dilation map. Otherwise, if R is between 0 and 1, L shrinks the plane, and we call it a contraction map. Of course, if R equals 1, then L does not change the plane. So it's what we call the identity operator. L of V equals V. So the function from R2 into R2 given by this, so L of xy equals x negative y, is also a linear transformation, as you may check. Geometrically, it acts as the reflection with respect to the x-axis. So what it does on the plane is it turns the plane upside down. Okay? The positive y-axis becomes the negative y-axis. The x-axis is fixed. A similar example is the function as shown, L of xy equals negative xy, which acts as the reflection with respect to the y-axis. So the positive x-axis becomes the negative x-axis and vice versa.